Hi everyone, welcome back and thank you for continuing to show up for your learning today. We're right here with a Desmos work-along video. That means you want to be done topic number 2, graphing the parent functions before you embark on this material. The exit ticket you're going to complete after this lesson, so don't worry about that part of it, but you want to know the unit circle and you want to have graphed the parent functions by hand and in Desmos first. So for right now, we're just going to do a very brief investigation of the roles of A, K, C, and D when we're transforming these trigonometric functions. So going back to our work on from Unit 2 on transformations. So like yesterday, we're going to change the scale. And this time we're going to see a little bit more of the y-axis because we're going to be a little busy on the y-axis, as it were. So this is a good scale for us. So go ahead and pause me and set up these settings and make sure it's in degrees. Otherwise, you'll just have a really squiggly line there. Okay, now we have here f of x is equal to sine x, and then I have another one, f of x, g of x is equal to sine x. I'm going to apply my transformations to g of x so that I can compare it to the parent function as I transform it. And let's start with a. A goes there. It's multiplying the output. So when I put this here, what that's doing is it's multiplying the value of sine x. And you can tell it to add a slider. Right now, a is 1, so g of x is equal to f of x. But as soon as I start changing a, g of x starts changing. Okay, I'll give you 5 seconds. What is that changing about the parent function? Is it the horizontal axis, the amplitude, the phase shift, or the period? You're right, it's changing the amplitude. So here, if I have a is equal to 2, we'll notice that all the zeros stay the same because they're stretched to themselves. 0 multiplied by 2 doesn't change. All the zeros are the same, but all the values of the function have been multiplied, stretched away from the x-axis by a factor 2. Okay, that is changing the amplitude, the distance between the maximum and the horizontal axis, or the minimum and the horizontal axis. Great. Okay, let's bring that back to 1. Oh, we'll also notice negative values of a reflect the function through the x-axis. Beautiful. Okay, set this to 1 so that we can look at yet another transformation. Now let's take a look at C. So we'll recall that A and C are affecting our outputs. They're affecting our y values. So if I add a C to this function, we can add a slider. There it is. Set it to 0 because we're adding 0. That doesn't change it. Boop, there's our parent function. All right, so C is adding on to the outputs. And if I add on to the outputs, let's say I add 2. What did that change about the function? Amplitude, horizontal axis, phase shift, period, 5 seconds. You're right, it changed the horizontal axis. It translated the whole function upwards, added 2 to every one of these points, and these are parallel. They'll never touch because there's always a space of 2 between them. And it effectively moved the horizontal axis to the line y equals 2. So there's a line that bisects this function. It goes straight through the function. Amplitude did not change, only the horizontal axis. Okay, so that's the role of C. Changes the horizontal axis. All right, now let's take a look at K and D. Now we're getting trickier. All right, so here, put brackets around your X, that. All right, and then your K's, and then actually we want a double bracket. K is going to come in here. Remember, K's and D's are affecting your inputs. So they're going to change things along the x-axis, whereas A and C change it on the y-axis. K does this, and D does this. A does this, and C does this. Okay, so now we're going to be working along the x-axis. So we're going to add the slider for K. When K is 1, we're saying multiply all my inputs by 1, please. So we'll notice that g of x is equal to f of x. That's why I can't see it. But as I change K, let's say I make K very, very large. Let's make K 10. Now, what did that change? Amplitude? No. The amplitude is the same. Horizontal axis? No. Phase shift? Actually, it starts at the same point and rises, so the phase shift is the same. The thing it changes is the period. Okay. When k becomes large, it compresses the function towards the x-axis. So let's go like just values just a little bit bigger than 1 here. So you'll notice, just take a look at some of those points. As I pull this in, and let's put in a line, actually. We'll put in a line here, y equals 0.5, y equals 1/2. So these are all, if you recall, the 30-degree points along here. And you'll notice that this one here, when I have y is 0.5, or sorry, k is 2, that this point here, and I'm just going to zoom in, you can zoom in too, this point here, 30, got pulled over here to 15. It's pulled by a factor 2 towards the y-axis. It's basically dividing all of the x coordinates by 2 when k is 2. If I go k is 3, we'll see that come to 10, because 30 divided by 3 is 10. So this is now here at 10. Okay, so it's compressing the function towards the y-axis. This affects the period of the function. We're going to see some mathematical formulas to do that soon. Okay, if k becomes small, like smaller than 1, we'll notice that, so there's 0.3, and that's moving that over to 10. Basically, it divided that by 0.3, so it became over here at 100. Effectively saying I need a value 100 in the x to equal what this one was giving me at 30. Okay, so that's when k is smaller than 1 but bigger than 0. It's stretching the function in the horizontal dimension. And then if k is negative, that's y. Yeah, sorry. When k is negative, then it also reflects through the y-axis now here. So you see that reflection through the y-axis. So when k is -1, it has reflected the function through the y-axis. Okay, pretty cool. Now set k to 1 so that we're not seeing that. And then we're going to add one final slider, x minus d. We often write this as minus. Sometimes I write this as plus. Really, it's a sign flipper. Just remember that d is a sign flipper. So what? What's going on? Why do I not see it? What has happened, everybody? Oh, because I need a bigger slider. Yeah. This is my scale. Okay. All right. So here you'll see like, well, I hardly get any effect from D. Okay. But what's that changing? Well, it's changing its phase shift. It's translating it left and right by tiny amounts. So if you click on these numbers, you could take this up all the way to 360. Okay. And then this could be as much as negative 360. Okay. Now we get a much bigger slider here. Okay. Now let's go play. All right. Now see that shift all the way from 360 to negative 360. What's that changing? The amplitude is the same. The horizontal axis is the same. The phase, the period is the same. What's changing here is the phase shift. Basically the starting point, or whatever this y-intercept is what we're really interested in there. So if I grab this, and let's say I want this to be equal to cosine. Well, I can pull that over so that I get that to be boop right there. Oh, there. Now it's a cosine curve. Okay. What do you mean, Mr. Jennings, that's a cosine curve? Well, yesterday you saw in graphing sine x and cos x that my lovely assistant here wanted to bombard you with knowledge and tell you that that cos x is just a translation 90 units left of sine x. Okay, here the red one is cosine x and the blue one is sine x. And if I just take sine x and translate it 90 degrees or 90 units that way, then it goes over there. So let's take a look at that. Zooming back in, coming over here. Notice that this is cosine now. Starts from there and goes down. But actually, we got there by just putting in, and these are all, just remember this is 1. This is just x minus, this is x plus 90 here, because this is minus 90. So this is x plus 90, sine x plus 90. F of x is equal to sine x. So just copy it down here. Sine x 90 is over here. See, that's equal to, this is equal to cosine of x. Sine of x is the same as sine of x plus 90. We see that with our trig functions and our translations. Okay, so now I just wanted you to be playing around at Desmos. Now, spend some time, create some wacky functions with your sliders, okay? See what else you can do. Zoom out a little bit, move yourself over here. You're not on your own screen. You don't see yourself. But here, try some different d values, some different k values, change the c value, and then change your a value. Whoa! And you can make some crazy functions, okay? And we can model lots of different things with these different functions, all right? Well, let's take a finer look at them in the next lesson, everyone. Send me any questions that you have by email or hit me up in the chat.